This talk is about promise problems and constraint satisfaction. The best example of that is promise coloring. Given a 3 colorable graph, can you at least find a 100 coloring, for example? So you're promised that the input graph is 3 colorable, but you don't know a coloring of it. And the question is, can you at least find something as weak as a 100 coloring in polynomial time? And this question is open. Another such problem was considered recently by Austrian Grusfami and Hostad. Namely, given its KCNF formula that is G-satisfiable, can you at least find a one-satisfying assignment? And here G-satisfying means that the assignment has to satisfy at least G literals in every clause. They proved that this problem is solvable in polynomial time if G over K is at least 1/2 and NP hard otherwise. And they dubbed this 2 plus epsilon sat is NP hard because it generalizes the fact that 2 sat is easy and then 3 sat is NP hard. As you see, these are kind of approximation problems, but we always compare some strong notion of satisfaction with a weak notion of satisfaction. And this allows to use some tools more usual for normal CSPs, such as abstract algebra. And this is one of the motivations for studying promise constraint satisfaction, is to introduce new views and new tools to approximation theory. In this presentation, I will talk about one such problem, but I will focus on this algebraic framework for proving hardness of approximation. So the problem we considered is very similar to the problem before. The only difference is that instead of a Boolean domain, we now consider any fixed finite domain. So variables now take values in a domain from 1 to d for some fixed constant d. The literals now of the form xi is in some set S. So these are arbitrary unary constraints. And then, as before, clauses are sets of k literals, instances are conjunctions of clauses, and G-satisfying means that we have to satisfy at least G literals in each clause. And the problem is again, given a G-satisfiable instance, find at least one satisfying assignment. In these problems, you could vary some of the definitions. For example, instead of one satisfying assignment, you could ask for a C satisfying assignment for some constant C, or instead of literals with any sets S, you could ask for some set of a specific size. But this turns out not to change much. All these problems with some fairly easy reduction turn out to be equivalent. So I will focus on this version here. And long story short, what we show is that the problem is solvable in polynomial time when G over K is over some threshold and it's NP hard otherwise. As you see, this generalizes the previous results because for the Boolean domain, for d equal to 2, this threshold is exactly 1/2. Nevertheless, to prove the hardness results, we had to use new tools. We had to extend the algebraic framework a little. So let's first see the algorithm. This is essentially Papadimitri's algorithm for 2 sat. It turns out to work for this problem as well. So we start with an arbitrary assignment, and while this assignment is not one satisfying, we randomly modify it. So we pick an arbitrary false clause, which means that every literal in that clause is falsified. So we randomly choose a literal from that clause, and we randomly choose a new value for the variable in that literal to make it true. And we repeat this over and over until the assignment we have is one satisfying. So this might seem quite naive. We're really not doing anything, just randomly changing the assignment we have until we satisfy it. But it turns out it works, and it finishes in expected polynomial time. The argument is a bit tricky, but also quite easy. Namely, we know there is some G-satisfying assignment Y. We don't know what this assignment is, but we promise there is one. So we can look at, in theory, what's the Hamming distance between our assignment and this assignment Y. We can calculate the probability in each step that this distance will increase and the probability that it decreases. And when you do that, it turns out that assuming G over K is over this threshold, that the Hamming distance will decrease in expectation. And even when g over k is exactly on this threshold, this means that the Hamming distance, the change in it, will be expected to be 0, but this means it's an unbiased random walk, so we also expect this to reach 0 in quadratic time. So that's the whole analysis. The algorithm itself is even simpler, so I think it's quite surprising that as soon as we cross this threshold, as soon as g over k is strictly less than 1 minus 1 over t, the problem suddenly becomes NP-hard, even though just before it had such an easy algorithm. This algorithm here is randomized, but we also have deterministic algorithms. One way to do this is by just running a linear programming relaxation. This works immediately when g over k is strictly larger than this threshold. When g over k is exactly the threshold, then we'd have to do some iterative rounding. But these are still fairly standard techniques. So we can now turn to proving hardness. As usual in approximation theory, we reduce from some version of label cover. If you don't remember, label cover is just this satisfaction problem whose definition only uses sets and functions. So we have variables. Every variable has a domain. Here the domain is called a set of labels. So for every variable we have to select one label from the set of labels under constraints, and the constraints here are functions, which said that if we select this label from L1, then we have to select this label from L2. This figure here is an example. You have sets of labels L1, L2, L3, some functions between some of those sets of labels, and I've selected satisfying assignment with green diamonds here. We select one label from each set, such that all the constraints are satisfied. As you might know, one version of the PCP theorem says that given a fully satisfiable instance, it is NP-hard to satisfy even just a small constant fraction of it. So for every epsilon, however small, you can even fix the size of the sets of labels to be some constant, and it's going to be NP-hard even to distinguish fully satisfiable instances from those where not even a small fraction is satisfiable. A slightly more combinatorial corollary of this is that the following is NP-hard. So given a fully satisfiable instance, it's NP-hard to select from each set of labels a subset of at most 7 labels, so that what you select for I intersects what you select for j after you apply the function pi. And why is that? Simply because if you could select such sets of at most 7 labels, then you could pick one of those labels at random, and then every constraint is satisfied with probability at least 1 over 49, so you've satisfied some constant fraction of all constraints. And we know this is NP-hard by the PCP theorem. So that's one corollary, which will be important throughout, so I will keep it on top of the slides. And with this example, I can state what the gist is of the abstract algebraic approach to promised constraint satisfaction problem. Namely, arguably, the fundamental theorem here is that every PCSP is equivalent to some label cover version. So to some problem of the following form, given a fully satisfiable instance of label cover, find a way to select for each variable I a something on Li, so that what you select for I agrees in some way with what you selected for j. And the something here could be many different things. For example, it could be subsets, and then we have something similar as above, except that the constraint here is not that what you selected for I intersects what you selected for j. It has to be exactly the same when you look at the image for pi. Another important example of what somethings on Li could be is distributions. So it could be distributions on Li. And this gives a version of label cover, which is solvable in polynomial time by linear programming. This will be important at the end. I'll return to that. But really it turns out to be interesting to look at this abstractly, that some things really could be anything. You only have to define how pi transform those things. This sets up a framework, for example, for showing hardness of approximation. What we have to do is we have to understand what the some things are, how pi transforms them, so what constraints they satisfy. Then we get some version of label cover, and what we have to do is just to show that this specific version of label cover is NP-hard. And the theorem gives us a concrete definition for what the some things are. For example, in our set problems, these will be functions with L inputs, which map G-satisfying k-tuples to 1-satisfying k-tuples. The exact definition here won't be important for this talk. It's only important that the some things will be functions with L inputs, which somehow encode those strong satisfying conditions and the weak satisfying conditions. So we have this version of label cover, which is NP-hard, and we know that set is equivalent to a version of label cover with polymorphisms, so with some functions with L inputs. So find a way to select for each variable I a polymorphism fi on Li inputs, so that pi of fi is equal to fj. Pi of fi here means the function you get from fi by you rewiring the inputs according to the function pi. And this has to be exactly the function fj. So how is this helpful? For example, you could consider the case when all polymorphisms are projections. So suppose we could show that all polymorphisms of sets are projections, which means functions of a very simple form, f of x1 to xl, just outputs one of the inputs. In that case, selecting selecting such a polymorphism is the same as selecting the label small l from the set of labels. So this would be exactly the same as just solving the label cover instance in the usual sense. And this is of course NP-hard. This is NP-hard even without using the PCP theorem. So this condition suffices, for example, for the problem of for-coloring three colorable graphs. In that case, the polymorphisms are projections. This is fairly easy to show, and because of that, the problem is NP-hard. This is not true for set, but there are some more general conditions. For example, if we could show that all polymorphisms of set only depend on a few inputs. So every polymorphism f is in fact just a function of some of the inputs, and all the other inputs can be disregarded. Then selecting such a function f is the same as selecting this subset of inputs. And as we know, this is NP-hard. It's NP-hard to select a bounded size set of labels from this set. So if we could show this, we would be happy, we'd be finished, the problem would be NP-hard. There are some other conditions. If we could prove that there's a small fixing set, for example, so a small set such that fixing some inputs there makes the remainder of the function constant, this would be enough. Or more generally, if you could fix some of the inputs such that the output avoids one possible value, and if you could show that there aren't many disjoint avoiding sets, then this would be enough to show NP-hardness. Unfortunately, none of these conditions are true for set. In fact, the closer you get to this threshold for G over K, the more badly all of these conditions fail. Instead, what we could prove for set is something a bit more subtle. We call this having small smug sets. So this means you could set some of the inputs to A and have the output A, even though all of the other inputs are different from A. The important thing here is that for a set to be smug, we only have to show it for one input vector. This turns out to be a little bit problematic, and let me explain why. Let's first see what happens when f only depends on a small set of inputs. So if f only depends on some small set s of the inputs, then I claim that pi of f only depends on the image of that set, pi of s. So on the figure here we have a set L of 5 labels, a set L prime of 3 labels, some function pi between them, and then pi of f is defined as follows. Pi of f on input x, y, z is defined as f of x, x, y, y, z. As I said, we just rewire the inputs according to the function pi. So if we assume that, for example, f only depends on the first 3 inputs, then we clearly see that pi of f only depends on x and y. So we have this exact correspondence that if f only depends on s, then pi of f only depends on pi of s. We'd like something similar for Smug sets. Unfortunately, it's not true. So for example, if f has a Smug set as here, so there is some input b1, b2, a with output a, then the problem is this input is not of the form xx, y, z in general. And this means we cannot deduce anything about the function pi of f. Instead, we have something in the other direction. If pi of f has a Smug set S, then the pre-image of that set is a Smug set of f. And you can check that easily. If you have this input at the bottom, b1, a, b2, then this induces an input vector at the top, b1, b1, a, b2, and we see that if this set of a's at the bottom is smug, then the pre-image of it is a smug set at the top. So we have this implication. The problem with it is that we're interested in selecting a small set of inputs. And even if we knew that the smug set S is small, the set at the bottom is small, then the pre-image of that set, it doesn't have to be small at all. It could be very, very large. So what can we show? So as I said, we can show that if S is smug, then the pre-image is smug. We can also show that every polymorphism has some small smug set of bounded size, and we can also show that there aren't many disjoint smug sets in any polymorphism. I won't show the proofs of that. These are quite tricky and quite specific to our problem. So let's just assume these are true for now. So we have an input, a label cover instance here, L1, L2, L3, some label sets, some functions between them, and we've selected in L3 a small smug set in green here. We can look at its pre-image, and we've also selected some small smug set in L2, and in general it's going to be disjoint from that pre-image. We'll look at its pre-image, and again we have some small smug set in L1, which could be disjoint from all the others. But we can repeat this over and over, and we see that at the top we always have those smug sets, those pre-images of smug sets, which are disjoint and therefore also smug sets. And we cannot have too many of them, so we know that at some point some two of them have to intersect. So this is what we can show. We can show that for every chain of length k in the label cover instance, there are some two levels, here L1 and L3, such that the small smug set we've selected for one level intersects the one we selected for the other level, after applying the function pi. And this is the version of label cover we have to show is NP-hard. In fact, we show something even slightly stronger. Given a fully satisfiable label cover instance, it is NP-hard to find an assignment such that at least epsilon of all k-chains have at least one satisfied arrow. So the gap here is even larger than in the PCP theorem. If the instance is fully satisfiable, then this means that in every k-chain, every arrow is satisfied. And instead, we require something very, very weak, that in a small fraction of all k-chains, just one arrow per chain is satisfied. And even this weak condition is NP-hard, as it turns out. The proof is not very hard. It uses known tools. Essentially, we start from the PCP theorem and we do parallel repetition. So once we know this statement, it's fairly easy to show, and this ends the proof. This shows that our problem, we started from the set problem. is NP-hard. So that's how the framework works. We have to look at polymorphisms of set. We have to show that in some sense they distinguish a small set of variables. We have to understand how the small sets of variables behave, and then we get some version of label cover, and we have to show that this version of label cover is NP-hard. That's the general framework. So I will end with some open questions. One question is, can we reconcile the analytic methods with the algebraic framework? So in approximation theory, analytic methods such as Fourier analysis or just probability theory or just basically any quantitative methods have been very, very successful, very powerful for hardness of approximation. And here we made it a point to avoid them, to introduce new methods, but it would be very interesting to merge the two. If you're looking for some specific problems, then of course there's the promise coloring problem, which is still open. So for example, is K coloring a free-colorable graph NP-hard for K at least 6? It's conjectured to be NP-hard always, but we really don't know. A similar problem is with promise graph homomorphism. For example, for coloring a graph that admits a homomorphism to a long odd cycle. And I mentioned this problem because polymorphisms here, we know the polymorphisms here are similar in some way to continuous maps from the L-dimensional torus to the projective plane. So it seems that algebraic topology could be very, very successful here. The problem is we just don't know algebraic topology too well. So if you want something more combinatorial, there's, for example, many hypergraph coloring problems. There's many variants, many results, many open questions. And last but not least, I wanted to mention that this is not only about proving hardness of approximation, it's also about algorithms. So, for example, Brandts and Cruz very recently showed that a certain combination of two algorithms works very well. So the first algorithm is essentially linear programming. I mentioned that when discussing those label covered variants. Those some things on L could be distributions on L, and that this variant of label cover can be solved in polynomial time by linear programming. And some problems can be reduced to that version of label cover, and therefore they are solvable in polynomial time. This is one way of showing that things are solvable in polynomial time. And this is possible, for example, for a set problem when G over K is below this threshold. This is solvable by linear programming. This can be rephrased as choosing those weights, WL, real non-negative weights that sum to 1. This is what a distribution is. In similar vein, instead of real non-negative weights, you could ask for integer weights that sum to 1. And then this version is again solvable in polynomial time by Gaussian elimination, and this again solves some other CSP problems. And it turns out that if you merge those two, if you do the two at the same time, with this condition at the bottom, then this is still solvable in polynomial time, and it turns out this solves many more problems. So the hope is, with ideas like this, we can find simple but very general algorithms that solve many different CSP problems. Thank you for listening.